and then I will post it as a YouTube video. Okay. Okay, so we're going to talk about some of the basic math issues that you're going to face. We'll do that for the first hour and a half or so, and then we'll do the lab, and then we'll go on from there. And I presume I don't have to talk about basic math. So we're going to talk about the kinds of math that we use. And some of the math needs to go back to calculating things like percentages and concentrations. And one of the calculations that is in some of the math has to do with calculating the percentage of active material in a drug mixture. So, for instance, if you were to dissolve 7 grams of drug in 93 milliliters of water, what is the percent concentration of the drug? Okay. A couple of things to consider. Remember that 1 milliliter of water weighs a gram. So we're dissolving 7 grams of drug in 93 grams of water. So we have 7 grams plus 93 grams. So we have a total of 100 grams of the mixture. Okay? So the concentration of the drug is 7 grams out of 100 grams, or 0.07, which is 7%. Remember, take the decimal and multiply by 100, give you percent. So that's how we calculate concentration. Remember, it is the ratio of the component that you want to know what the concentration is to the entire drug sample. So including it. So it's not 7 over 93. Okay, that's a common misconception that people have. So this applies whether we're talking about creams or solutions or dissolving or mixing liquid and liquid. It doesn't matter. Okay, we mix these things up. Concentration is dependent on the total amount of material. Now, a lot of times we'll have, we'll be given a prescription and we have to figure out how to fill it. A prescription might look something like this. Okay. Okay. Prescription should always have certain information. Prescription information should always, of course, identify the drug, but also it should identify the amount of drug per dose, the route of administration, the number of doses per day, and then the number of days that was supposed to, days supply was supposed to be. Okay, the first clue is that we have to figure out how many units, whether it's milliliters or tablets or capsules, how many units the patient is going to take per dose. And here, the drug is propranolol, which is a beta blocker. It's used, it's an old drug, but still commonly used to treat things like high blood pressure. And so, first off, PO. That means it's either going to be tablet, capsule, or potentially even an oral liquid. In this case, we're going to assume that we have tablets on our shelf. And we're going to say that first thing we do is we look for our stock. What's in our stock? These things come when they're delivered to the pharmacy. They're usually in large bottles, often as many as 1,000 or more units in a bottle. So obviously, we have to pull this out and then take it out of the stock bottle and then provide it to the patient. So what we're going to see is we're going to see that on the shelf, our stock is propranolol tablets, 15 milligrams. I'm making this up. I'm not even sure that propranolol comes in that strength, but nonetheless, the principle is that we want to know that. So, what's the important information here? Okay, first we have 2 steps to fill a prescription. Step number 1, how many units per dose? Okay.
Would be the 15 milligrams per dose, right?
What?
15 milligrams per dose?
No, it's 30 milligrams per dose. Yeah, that's pretty clear. We're gonna go through the calculation because sometimes it's not so obvious. We just saw an example where you can have a half a tablet as a dose. Okay, so keep in mind that sometimes if you look at a tablet, you'll see a score. If you look at it from the side, it's like a groove cut into the tablet. And that means that the tablet is designed to be broken in half. Now, we don't break them in half in the pharmacy. That involves touching the tablet. We never directly touch a tablet or a capsule. But they're designed for the patient to be able to do that. And they can do it either by putting it on a counter and pushing on either side of the groove, or they can spend a few dollars and get a pill cutter. I've always been too cheap because a pill cutter isn't really necessary unless they're not scored. Again, doctors can prescribe any dose, any drug, at any dose by any route of administration that they want. Just because the pharmaceutical company produces one type of tablet doesn't mean that that's what the doctor is. It's what we in the pharmacy may be restricted to giving the patient, but if they can be broken, they are broken. So we will do that sometimes. So the first question is how many units? In other words, in this case, how many tablets per dose? You've already identified it, Cheyenne, but I'm going to give you a simple formula for calculating. Number 2, how many doses per day? And number 3, how many days? So what we have to do is calculate the number of units per dose, then multiply that by doses per day. That's how we fill it. So how do we calculate the dose? There's lots of ways. I'm just going to give you a formula. There are lots of ways in your book, all of them algebraically rearranged to this form. So instead of approaching this from a pharmacist standpoint, I'm approaching it from the standpoint of a mathematician. And formulas are easy to use. If you remember something, X, which is the number of units of drug per dose, okay? Equals D times V over H. Okay. This will solve by itself many of the dosing questions you have. It will actually solve all of them, but you may have to work with the information, make some changes, convert units, convert a few other things. We'll go through that because we'll go through a little bit more of that in a bit. What is D? D is the dose. Is the dose prescribed by the prescribing person. So in this case, this is D, 30 milligrams. That's what was prescribed by the doctor. Note that we just read this off the prescription. There's no real question about what it can be. V is the vehicle. This can be a little confusing, so I'm going to give you a couple of ways to think about that. The vehicle means how is it? In this case, the vehicle is okay. So where do we get that? We get that off the label of our stock bottle. So again, we're just reading it. So V is tablets. If it's a liquid drug, okay, so for solids, it's a tablet or a capsule or some other solid dosage form. Okay. For a liquid, it is always, and I'm going to capitalize this even though, you know, if you go back to your email guidelines and text guidelines, that's like shouting, right? But it's something to remember. Always. If it's a liquid, it's always a volume in milliliters. Always. Okay. In this case, it's a tablet. H is the potency or amount of drug in the vehicle. So H in this case is 15 milligrams. And again, we just read that off the label of the drug. So none of this requires that to do. Morning, Katie.
Good morning. How's everyone doing?
Everyone is fine.
This one's the TV. I can so we didn't get right. Thanks, bye.
Thank you, Katie. All right. So now we just take these values and plug them into this formula. So we have X equals 30 milligrams times tablet over 15 milligrams. Milligrams cancel, and 2 tablets per dose. So when we write out our instructions to the patient on the prescription label, we say take 2 tablets twice a day.
since it's a BID dosing. Right? So now we've done one half of the work. Because now to fill a prescription, we have to calculate the total number of tablets that we need to give to the patient.
So we have now 2 tablets per dose times 2 doses per day times 30 days. Days cancel, doses cancel. The only thing left now is tablets. So 2 times 2 is 4, times 30 is 120 tablets to fill the prescription.
The questions, many of the questions you have will be exactly that. So we simply gross it out. It looks, do you have any questions about that? I want you to remember that formula, D times V over H. But I also want you to remember that V is going to be either tablet or capsule or a number of milliliters. And it doesn't matter if they're liquid drugs, it doesn't matter if they are oral liquids or injectable liquids. But invariably, at the end of the day, what we want is a number of units, either tablets, capsules, milliliters, etc., that we're going to give the patient. Okay? Make sense? All right. Let's do something a little bit different. Let's go to a liquid drug. We're going to start off with an oral liquid. To use amoxicillin. So we have amoxicillin, 125 milligrams, PO, PID, 10 days. PID is what? 3 times a day. Okay? Three times a day. So we look on the shelf and we find amoxicillin suspension, 250 milligrams per 5 milliliters. Now, amoxicillin comes in many different dosage forms. Tablets, capsules, and there is the suspension. Generally speaking, we're going to look and see who the patient is. Obviously, if the patient is a small child, we're not going to give them a tablet. We're going to give them a suspension. If the patient is an elderly adult who has trouble swallowing, they may request the suspension. Okay. But we actually look to see, we're going to assume in this case it's a tie. So we're going to give them an oral dose. You've all probably had the experience of using this stuff already anyway. Okay, so once again, let's
let's go back and look at, we want to go back to our formula to calculate the amount of drug needed for a specific dose. So, first off, what's D? What is D in this case? What's the dose prescribed? 125, right. So that's D. Okay. What are V and H?
H is 250.
H is 250.
And V is 5.
Right. And V is 5 milliliters. Okay. Again, for a liquid drug, the vehicle is always a volume in milliliters. It is not solution, suspension, etc. It is a volume in milliliters. And we take it straight off the label. So now we have a fairly straightforward solution here. 125 milligrams times 5 milliliters divided by 250 milligrams. And remember, use your calculator. So what's the answer? What's the amount per dose for this patient? Right. 2.5 milliliters per dose. Now, once again, to fill the prescription, we have to multiply that by the number of doses per day. So 2.5 times 3 is 7.5. And then we multiply that times the number of days. 10 times 7.5 is 75 milliliters. That's how much we dispense to the patient. And remember, for the most part, we're going to tell the patients, or the person actually giving the drug to the patient, usually the parent, usually the mother, to give them a dose of 2.5 milliliters. But many people need to be told the dose in teaspoons. And remember how many milliliters per teaspoon?
4.9.
Yeah, we've rounded off the top. But you're right, absolutely, 4.9. And that can be important in some cases, but for the most part, the difference between 4.9 and 5 is so small that it's not worth it. Okay, so 5. So we now multiply this by 1 teaspoon per 5 milliliters. Milliliters cancel out, and we get 1/2 teaspoon per dose. That's what we put on the label. Give 1/2 teaspoon per dose. Now, fortunately, but nonetheless, we do that for convenience. We also give them a dosing, a little hollow handle spoons, or little cups, or even an oral syringe. Right? So that we can squirt it into the mouth. So we can do that a lot of different ways. But note that the only difference between this problem and the other is we have a different vehicle. We end up with an amount per dose in milliliters instead of tablets. Now, all the calculations are exactly the same. So the key with all of these is to identify the date. Once you've done that, the rest is simply punching numbers into your calculator. Sometimes it's pretty obvious, and that's great, but we encourage people, at least initially, to use the calculator. When you are working in a pharmacy, you have to. If you take the pharmacy technician certification exam, they give you a calculator to use in the exam.
They do not allow you to take your phone in. So be aware of that.
All right, questions?
So one of the questions asking, how much of the drug should, must be used, to make 612 milliliters of a 5% suspension,
Okay.
which
All right. Let's
5%.
okay. Let's go to that. Okay.
Now, remember that when calculating the percentage, okay, we're looking at the weight, or if it's a liquid mixture volume, of active over total weight, which is active plus inactive materials, right? That is a fraction, or that will convert to a percent. Okay? So what happens is, if you want to know, if you know the percent you want, okay, amount of active, we can actually write that down as an equation that says the percent as a decimal times the total amount of material. Okay. So if we want, say, 100 grams of a drug mixture that's 10%, we multiply 0.1 times 100. 5% would be 0.05 times whatever the number was. So what we want is, we have to know certain things. We have to know either the weight of the active and the percentage, or the weight of the active and the total, or the total and the percentage. If we know any of those. So what we have is a little, the formula that I give right here. Weight of active over total weight is the percent. We can call that X if you want. But the weight of active over the total, if you divide that, it's going to give you a decimal. Convert that to a percent, right? So if we know any two of these, we can calculate the third. So as I said, the amount of active is the percent that we're looking for as a decimal times the total amount of material.
So if it was 5 suspension, it would, and the total is 612. We do 0.05 times 612,
Exactly.
and then 306 over 612. So 306 would have been the answer.
5% of 612, 0.05 times 612.
It's 306.
It's not going to be 306. No, if you multiply that out on your calculator, 0.05 times 612, you're going to get 30.6.
So yeah.
Okay. Careful with those decimal points. They'll kill you every time. That's why I like when you're doing things, especially on a calculator, I like to see you do the calculation at least twice and make sure you get the same answer both times. Again, when you said that, I knew it was wrong, but that's because I've done enough of these calculations that I have a feeling
And that only comes. You'll all learn that ultimately, but it comes with practice. So, did that help?
Mhm.
Okay. Okay, about what, Shine?
So.
Where did I lose you?
use this one for the substantial one.
Uh-huh.
So 610 milliliters, when I put that in weird actions.
That is, no, the 612 milliliters is the total of the drug. The total, including the active.
Okay, so how do I figure out the
Okay? The amount of active is the percent, or converted to a decimal, obviously, the percent times the total amount,
Oh,
Okay.
okay.
right? That makes sense now?
Yeah.
All right. Yeah, again, it's just remembering when someone says percent of, that means you're going to be multiplying by the decimal equivalent of the percent. Of means multiply when we're talking in this context. Okay, does that make sense to everyone?
Yeah.
Glennis, are you getting this? Okay. Okay.
Yeah.
Okay, let's go ahead and take our first break. This is actually a good time to stop. So I'm going to pause the recording. We'll pick it up again later. Okay, so we're recording now. All right. So there's two more things I want to talk about before we do the lab, and that is IV calculations and mixtures, because those are two important things. IV drugs are administered by two potential routes. One is the bolus route, and the other is infusion. Bolus means basically you stick the needle in, you squirt the contents into the patient, you pull the needle out. So drugs that are given by intramuscular injection and subcutaneous injection are given by that route, bolus. But IV drugs can be given either that way, or if we need a drug, a large volume of drug over time, we do this by infusion. Infusion is just a word that means a volume over time. And there's two ways that we do this. One is to use an infusion pump, which is going to be delivering milliliters per hour. So when we're doing a calculation involving a fusion pump, our ultimate answer is in a number of milliliters per hour. Or drops per minute. This is in the case of not using an IV pump, but hanging a bag and letting gravity do the work for us. So they both will deliver essentially whatever amount we want. It's just our calculations are mostly exactly the same. By mostly, I mean when we are doing the gravity, we have to calculate milliliters per minute and then change that to drops by using what we call a drop factor. I'll get to that in a moment. I'm going to give a couple of fairly straightforward examples. One of which is to administer, we get a prescription for an IV antibiotic. And that's going to be cephalosporin, 200 milligrams. No.
500 milligrams IV over 2 hours. Okay, now that means that our dose to the patient, D, now becomes 500 milligrams for 2 hours. Okay. That becomes D. Note that the time factor has to be in there for infusion, because infusions are always given over time. So we look on our shelf. And we find cephalosporin's sterile injection. This is a solution in an IV bag. Okay. Cephalosporin sterile injection, 1,000 milligrams per liter. Okay. Now, we can use dV over H. Okay. We can use dV over H to solve this. D is 500 milligrams in 2 hours. Let's change that now by dividing by 2 to 250 milligrams per hour. Okay. So we have 1,000 milligrams in 1 liter, which is also going to be 1,000 milligrams per 1,000 milliliters. Because remember, we give by milliliters per hour. Okay. So this becomes V and H. Right. So we want to deliver 250 milligrams per hour, that's our D, times 1,000 milliliters, that's V. H is 1,000 milligrams. Note that the number of milligrams cancel, 1,000 cancels, and our answer is 250 milliliters per hour. Okay. So when we prepare this drug for a patient, we send it up to the food ward with instructions to infuse at 250 milliliters per hour, 2 hours. Okay. This calculation works for almost all of our IV infusion problems. Pretty straightforward again. But like anything else in medicine, what we have is some more complicated problems. And by complicated, I only mean there are some other steps to take. The calculations are no more difficult than this, but there are a couple of other steps to take. And so I'm going to put up another formula for another problem. And I'm going to, let's see. Just going to call it drug. I'm not going to call it, I'm not going to give it a name, but drug. Um, 5 milligrams per kilogram IV in 250 milliliters over 5 hours. Now the question here is, what does it mean when we say 5 milligrams per kilogram? But I
was raising my hand, but
oh, okay,
5 milligrams per kilogram.
per kilogram of weight. When we see something like that, there's one thing that we know, and that is that we have to determine the weight of the patient in kilograms. Because we have to multiply this dose, 5 milligrams, times the number of kilograms the patient weighs. Would be 5 milligrams itself would be the dose to a 1 kilogram patient. In other words, a premature baby. So we have to be multiplying times the weight of the patient. So where do we get the weight of the patient? We go into the patient records. Working in a hospital, we have access to the patient records. So we go into the patient records and we find out what he weighs. In this case, we're going to say that the patient weighs 176 pounds. Okay. So remember what the conversion of pounds to kilograms is? 2.2. Remember, we've got kilograms, pounds, 2.2. If we're going in that direction, we multiply. If we're going in this direction, we divide. Which reminds me. Did you get a copy of this? I didn't think so. I was thinking that you were gone when I finished it out. That is a conversion rubric. In each case, we start with the larger unit on the left, smaller unit on the right, and this allows us to convert from larger to smaller by multiplying. Depending on the number of those arrows we pass over, we multiply by each factor, or divide if we're going from right to left, from smaller to larger. So we're going to divide this by 2.2 pounds per kilogram. Pounds cancel out. The answer is in kilograms. What is the weight of the patient in kilograms? $80. And so now D equals 5 milligrams per kilogram times 80 kilograms, which is 400 milligrams of the drug. Okay. So one way or another, we want to be able to get this to the patient. Let's say we look on our in our stock solutions and we don't have this drug. But what we have is a solution of the drug at 500 milligrams per 5 milliliters. Okay, our stock solution. What we have to do is take some amount of that drug out of that stock solution and put it into a 250 milliliter IV bag. And so, again, we're going to use D times V over H. In this case, D, we've already calculated, is 400 milligrams. V is 5 milliliters, and H is 500 milligrams. So our dV over H calculation becomes 400 milligrams times 5 milliliters divided by 500 milligrams, which is going to be 4 milliliters. So we take 4 milliliters of this stock solution by a syringe out of the vial that it's in, and then add it to the IV bag to make our 250 milliliters. Okay. So we have often several calculations, but you do note that in each case, dV over H works. But we have to remember what is D, V, and H for each of these calculations. Okay, so now we know we have 400 milligrams. Okay, and it's going to be in 250 milliliters. So what is the rate of delivery? Well, here we have one other formula, which is, we're going to make this a pi. V, R, and T. Volume equals rate times time. Rate is always a volume per unit time. The total volume is calculated by multiplying. Or if we know the volume and we want to know the rate, it's volume over time. Okay, so this formula, V equals R times T, R equals V over T. We can also calculate the time if we know the volume and the rate. T equals V over R. So time equals volume over rate. If you remember this little pi, you will have those formulas, those little equations, always. Okay, so in this case, we want to know the rate. Rate is volume over time. We have 250 milliliters over 5 hours, and that's going to be 50 milliliters per hour. Does that make sense to everyone? Okay. You will find that there are several math PowerPoints. I have tried to record my teaching sessions as well and put links in those to Zoom, and there's one of them that's in there by YouTube. This one, today's, will go into a YouTube video, which I will upload after I get it converted after we're done. Okay. All right. So anytime we're dosing by weight, we know we're going to be multiplying by the weight of the patient. So we have to know the weight of the patient either in kilos or in pounds, which we can convert to kilos. Okay? So that's something to remember. Let's take another problem. Okay. Sometimes you will see a prescription or medication order from the hospital that will be something like this: nitroglycerin IV 0.3 micrograms per kilogram per minute. You note that there is no time limit on this. So this is a continuous infusion that will continue until the doctor cuts off the order. Again, we need to know the weight of the patient. We need to know the amount of material we're going to be infusing, the total material. So we need to find a stock solution. In this case, we find on the shelf, we find that we have bags of nitroglycerin at a concentration of 400 milligrams in 500 milliliters. So what we have now is to identify a couple of things here. One is D, we already know 0.3 micrograms per kilogram per minute. We know that V is 500 milliliters, and we know that H is 400 milligrams. I'm going to point out something. We cannot have micrograms and milligrams in the same equation because we have to have the same units. We can either convert micrograms to milligrams or milligrams to micrograms. My rule of thumb, and that's just my rule of thumb, is to always convert to the smaller. One of the reasons is that you're always multiplying. And I, just like almost everyone else on the planet, multiply better than I divide. So I always go to the smaller unit. I don't care which direction you choose to go. But I suggest that whatever you choose to do it the same way every time. Because by doing things by the same methodology, you avoid errors. Okay. So I've got this, but I need to play with dose because I don't know the weight of the patient. And if I'm working with an infusion pump, then I need to convert minutes to hours as well. So if I'm going to work on that. So the patient weighs 132 pounds. How many kilos is that? Okay. All right. Now we just discussed the fact that if you're dosing by weight, you multiply by the weight of the patient. So D now gets multiplied by 60 kilograms. We're going to assume we're working with an infusion pump, which means we want milliliters per hour. So we now have to multiply this by 60 minutes per hour. We need to get rid of the minutes. So anytime we are using an infusion pump and the dosing is per minute, then we know we're multiplying by 60 as well. So what is 0.3 times 60 times 60? Use your calculators.
What are we looking at?
Pardon? We're at 0.3. We're multiplying it by 60 and then again by 60.
1,080.
So we have 1,080 micrograms per hour. Okay. Now we're going to convert milligrams to micrograms. What's the conversion factor? Pardon?
Can you ask that again?
Okay. How do we convert milligrams to micrograms?
2 times
By what?
100.
1,000. Yeah. Remember, that's 1,000. Use that rubric sheet I gave you. As far as I'm concerned, cheat sheets are acceptable. I'd rather you get the right answer. Times 1,000 micrograms per milligram. We're going to get 400,000 micrograms. Now, that looks like a pretty big number. And it is. But calculators don't care, which is why we use calculators. When you are using big numbers, though, make sure you count the zeros. Don't forget that. So now our formula becomes 1,080 micrograms per hour times 500 milliliters over 400,000 micrograms. Micrograms cancel out. And what's our answer?
Hmm.
Five point four. 5.4 milliliters per hour. Everybody understand how I got that? Or that was derived?
Is it 1,080
1,080
times 500?
times 500 over 400,000. Do you get the same number?
One zero eight zero times 500 equals 510,000 divided by 400,000. 1.35 square.
You got 1.35. Okay. Want to do your calculation again, China? So we have two different answers, so now we check it.
Just the last one.
Pardon?
Just the last one, the 180.
1,080.
1,080.
Yeah.
I did one 100,000, so 400,000. I
Ah.
thought it was a 1.
1.35. Okay. This is a sample calculation. That's an unusually low rate, but it's not impossible. But, does that make sense to everyone how we got there? Okay, so we directly calculated the flow rate. All right. So, let's see. All right, so we're going to have to wind this up. I want to do a mixture next. A lot of times we're asked in the pharmacy to prepare a mixture that does not exist in our formulary. A lot of times that can be either a cream of a concentration that's not normal. We have a lot of creams out there, but just because the pharmaceutical company develops a cream at 2% doesn't mean that's what the doctor wants. So we may get a prescription that says something that we don't normally have. The example I'm going to use is that we are asked to prepare 500 milliliters, 7.5% dextrose. Okay. We don't have that on our shelf, but we do have other concentrations of dextrose. We have 5% dextrose, and we have 50% dextrose. And we want to know how much of each of those need to be mixed to give us 500 milliliters of 7.5% dextrose. Okay. Now this may look a little complicated, but there is a little rubric we call the alligation alternative. And it starts off as a tic-tac-toe board. Again, I'm going to construct two of them. One for the theoretical and one for the practical here. So when we're constructing this, we start with the target concentration in the center. So what's our target here? What are we aiming for? What have we been asked to prepare? That's a total volume. What's the percentage we're being asked to prepare? 7.5. So we put it in there just as 7.5. We don't say percent. We don't say 0.075. Just a percent. In the upper left, we put the percentage of our high starting material, which is going to be what? What's our high concentration starting material? 50 is the high number. Okay. In the lower left, we put our low concentration starting material. Okay, which is? It's 5 now. Okay, so now to complete this out, we do a little cross. We have in the upper right the difference between the target and the low starting material. So what is the difference here between the low starting material and the target? So we're subtracting.
7.
This is 0, this is 5.
Oh, 2.5.
2.5. So it's the difference between the target and the low. Over here in the lower right, it's the difference between the high concentration minus the target. So what's the difference between 50 and 7.5?
6.5. 46.
46.5?
I did that on my head.
Yeah. Let's go ahead and use your calculator.
42.
42.5. Okay. So what this is the number of parts of the high concentration material, and the bottom number is the number of parts of the low. So we need to know the total number of parts as well. So what's the total? So we add up the right-hand column. So what's the total of the right-hand column in our problem? 45. How do we use this? We say 2.5 parts, which is 2.5 out of 45. And the second one is 42.5 parts out of the 45 total. Okay. So we divide the number of parts by the total. And this gives us a fraction, which we then multiply by the amount of material requested. In this case, it's 500 milliliters. Okay. Now, does that make sense to everyone? When we're setting up fractions, remember, think of it as a pie, in this case with 45 pieces. Okay. We take 2.5 pieces, and that's one of the components. But we need to know how big the pie is. If it's a little pie like that, everybody's going to get about a quarter of a teaspoon, a taste. But if it's a pie that's this big, 45 pieces might be a fairly substantial serving. Okay, so that's what the total size of the pie is that amount requested. Somewhere in the problem that you're solving, you'll be told how much material is being requested. Sometimes it'll start out at the front of the problem. Other times it may be told at the end of the problem. But one way or another, you will get that. So what we do is we now have 2.5 divided by 45 and then multiply that times 500. So what is that?
So 2.5 divided by 45 is 0.048888.
Yeah, times 500 now.
So
Don't round it off.
it's 24.44.
Okay. Equals 24.4, etc. milliliters. This is the number of milliliters of the high concentration. In this case, we're going to mix 24.4 milliliters of 50% dextrose with what? So we do the same thing below. 42.5 divided by 45 and then multiplied by 500.
472. 22.
470,
2.22.
okay, then you need to check this number because they really need to add up to 500. Check both numbers again. 2.5 divided by 45. Let's look at that.
42.
Pardon? Yeah. 42.5 divided by 45 times 500.
So it's 472.
472.2. Okay, so I'm going to ask you to check this calculation again because this only adds up to 496. It needs to add up to 500.
So the top one is actually 27.7.
27.7. Good. See, there is an example of why we 27.7 plus 472.2 is 499.9, which is just fine. Okay.
That's round. So that's one of the checks you have. When you do the two calculations, make sure they add up to the amount you're looking for. And then if they don't, go back and recheck your calculation. But that's how we solve all. It doesn't matter if we're talking about a cane where we're measuring everything in grams or a liquid where it's all measured in. Okay. So questions? There are a number of allegation problems in math week 3. So all of them can be solved using this formula. If you forget how to use it, go back and look in there's a section on allegations in your textbook, and there's the PowerPoint. Okay.
So if I were to have an answer, so whatever divided by whatever times whatever, well, yeah.
Right.
And it had 0.09. How far are we going to go with decimals?
If you're, I would round it off to 0.1. Yeah, I would.
Oh, okay. That's perfect.
Makes sense now?
Yeah.
Okay.
If we ever get a number, will we ever get a number that's just a little bit higher?
Rounding usually ends up when you're going to be either a little, like a tenth short or maybe a tenth over because of rounding. But it shouldn't be any further than that. Okay? Okay? All right. Let's see what time. Yeah, let's take a short break and then come back and do the lab.